Good day, everyone. It's your friendly professor here, Nate Allen, coming at you with section 5.1, quadratic functions, aka parabolas. So quick bit of notes, explanations about how these things are. You should be familiar with these already. You've definitely seen this in Algebra 1 and more so in Algebra 2, but we just want to review it, get into a little bit more detail about things. And of course, I always like to elaborate and give you a little bit more. So try to show you why some things are what they are, to add a little bit more than just, hey, remember parabolas, remember the basics. Let's dig a little bit deeper. So let's start by talking about the general form of these quadratic equations or functions. So in general, we have something where it's f of x or y equals, because we know it is a function. It passes that vertical line test, only hits in one place everywhere. And when you see the x squared as your highest exponent, we call it the degree of a function or equation, then you know it is what is called a quadratic and will therefore be a parabola. Now there's one key place on the parabola, on these quadratics, that we want to be able to find and find quickly to help us graph, and that is what is called the vertex. So there is a thing called vertex form or standard form, because we would much prefer this than the generic form, because it gives us the vertex in standard form. So I often just call it vertex form, so you know exactly what it gives us. And remember, the vertex is that point on our parabola. As you can see here, graphed is the generic parent graph that we already reviewed a couple sections back, y equals x squared, where if I stick in anything for x and square it, I will get out my y value. 0, 0, 1, 1, 2, 4, or negative 1, 1, negative 2, 4, and so on. Well, then that point where it changes from what is called a decreasing to an increasing is very, very important to us, not just for quadratics, but all functions, especially in calculus. It would be so critical for us to find that value, what in this graph is called a minimum, that we're going to call it a critical point. Okay, so what I want to show you is that this vertex or standard form gives us the vertex, and all you have to do is figure out what would zero out that x squared piece. So that's why we use different letters, h and k, instead of the coefficients a, b, and c. So the a is going to give us some information, but the key to this is that h and that k to find our vertex. And to find our vertex, like I mentioned, we will take whatever the squared part is and find when it would give us a 0. For what x value? Hopefully you can see pretty easily that what minus h would give us a 0? Well, that would be h. So just like we talked about before, when graphing all the parent graphs, x's are x's because they wanted the opposite of us. Okay, so take whatever's the opposite there. Now remember, if there is a number in front, you're going to have to do even more. So that's why in general, we just say set it equal to 0, and that will give you the x part of your vertex. Because if I plugged in h for my x value, I'd get h minus h, which is 0, squared is 0, times anything is still 0. So all this just goes to 0, which means when we plug this in, we will get a y value of k. So remember, x's still want the opposite of us, and y's are y's. We do what they say, exactly as written. +3, -2, whatever it might be. Okay, so that is a very important piece to this puzzle that is called a quadratic function or parabola. So now that we have that, let me show you why this and this can also be used, even though we don't want to necessarily use this, to find that vertex, that key value where it changes directions. So as you can see here in some of the notes that we've written up, in that generic form versus that standard or vertex form, we know that their y values are equivalent. So if we wanted to know in this generic form what that vertex value would be without rewriting this in this standard form by a little thing called completing the square, which we can do, I'm going to show you an alternative way as to why our h, or the x of our vertex, is actually equal to negative b over 2a. It's very simple to prove, but a lot of people have never seen this, so wanted to show you that we know that a times the x minus h quantity squared plus k is equal to my other y value. In other words, we know that this and this are equal to the same thing, so therefore they are equal. So now all I'm going to do is take this and expand the left side. So I will have to square this first, which means that times itself. And doing that, I get x squared minus 2xh plus h squared. Now I'd have to distribute the a, which gives me ax squared minus 2axh plus ah squared. And then we have plus our k. And we still have it equal to the ax squared plus bx plus c. So what we then know and are able to do is kind of manipulate this to make it look like the other thing, because we know that they are equivalent. So if I take and try to make the left side look like the right side, I then have something x squared plus something times x plus some constant. So if I rewrite this in a different form, I end up having that something times x squared. And then I want the thing that has the x by itself. And I'm going to write plus a negative 2ah times my x plus all the other stuff that doesn't have x's with it, which would be my constant. So we get the ah squared plus k. And since we know that those are equivalent, then we can take this and know that my b and this negative 2ah have to be the same. And if that's the case, we go ahead and rewrite that over to the side here, and we find out that, well, if b is equal to the negative 2ah, then I can solve for the h by simply dividing by the negative 2a. And that becomes positive 1, or h is equal to negative b over 2a. And that, my friends, is why we take that generic form, and to find the x in our vertex in standard or vertex form, we call it the h. We take this and we say that that x of our vertex is equal to negative b over 2a. But now you know why. Okay, I could do the same thing and solve for the k in this equation, but as you can see, it would be much uglier. So what we say is, well, since they're telling us what the y is equal to, as long as we know what x is, we will just take that thing and plug it in there and there to see what comes out and find our y. So we say in this form, to find our vertex, we will simply do the negative b over 2a to find our x. And then once we have that, we will plug that in everywhere we had an x to find our y value. Just trying to be clear and review, but also give you a little bit more something so that you understand why these things are what they are. Not just, oh man, we're really going to confuse the students by doing this and then trying to switch up letters and switch the form. No, it just depends on how it's given to you, right? So hang in there. Make sure that you know both of these different types of functions that are both quadratic, general versus standard form. and how to find that very important point called the vertex. Because now we're going to talk about more things that pertain to these parabolas, these quadratic functions, not just that most important point called the vertex. When we go to build or graph these things, obviously we want to start with that point. But here's what's cool about parabolas or quadratic functions. Whether they're facing up, down, they're more narrow or more wide than normal, which all, by the way, depends on A being positive or negative, because that's the thing in front of the x squared that makes it a parabola. But also if that A is a 1, then it's got that normal curvature where we go out 1 squared is up 1, out 1 squared is up 1, or out 2 places, squared 1, 2, 3, 4, out 2 places, up 1, 2, 3, 4, 3 places, 9. If it's something other than that, say it's a 2 in front of the x squared, then it's going to go up twice as fast. So instead of going up 1 when you go over 1, square that and double it. Instead of going over 2 squared, which would be 4, double it. It'd be up 8. So you could see it would be even more narrow. Or it could be half as big and be wider. So that all has to do with the A, the thing in front of the x squared, the coefficient we call it. Whether it's in that form or this form. It's the thing in front of the x squared, because that's what makes it a quadratic or parabola. But what else is cool is that when we go right 1 or left 1, when we square it, we get the same value. Right 2 or left 2, we get the same value. That, my friends, is what is called being symmetrical. And there is an axis of symmetry or a line of symmetry that we know every single one of these, no matter where we're at, would be the same distance on the right as it is the left. So that's another important piece to graphing these perfectly. And to help with the width of these things, we often like to find the x-intercepts, which, if you remember, the x-intercepts are going to be where the x is some number, but I'm not up or down any for my y value. But it could be another x over here, still not going to be up or down any at that point. To find the y-intercept, exact same thing, but in reverse, the inverse. We would then see, well, at this point, which is where it crosses through the y, it's not right or left any. So the y-intercept then would be where we're trying to find the y when x is 0. To find the x-intercept or seps can be 0, 1, or 2, typically 2, every once in a while 1, and 0, but to find those x-intercepts, we'll let the y be 0 in order to find our x. Now, what about the domain and range that we discussed with all of our parent or toolkit functions? Still, our x values or inputs, our y values or outputs for the domain and range. So with parabolas, whether they're facing up or down, they will slowly go out forever in either direction. So our domain will always be all real numbers, or in interval notation, negative infinity to positive infinity. But our range will not. Our range will depend on the y of our vertex, or the k value in our standard or vertex form. Okay? It will also depend on not just the y of the vertex, but also the direction of our parabola. If it's facing up, it's going to go up forever. So remember, smallest to biggest on our y-axis, which means bottom to top. When do I start hitting my y values? Well, notice my vertex on this would be 1, -4, and it starts at -4. And it goes up all these y values to infinity. Now, if it was facing down, it would start, since it goes down and out forever, at negative infinity. Remember, we never include infinities, all the way up to a high point of -4, which would be included. Okay, so that range depends on two things, on the y of our vertex and our a, the coefficient of x squared, and whether it's up, positive, or down, negative. Lastly, what about the max or min? And don't forget, our axis of symmetry, by the way, is a line. Therefore, you have to give me the equation of this line. And what's true about every point on that dashed line? Well, the x's, notice, are always the same, but y can be whatever. So you're going to tell me where x is equal to something. And by the way, notice that axis of symmetry will go right through our vertex, which means it will be equal to the h, or x, of our vertex. But don't forget to give it to me as a line, which is what it is. So that brings us to the last thing, maximums and minimums. Where are those going to occur? Again, the almighty vertex. So very important. That's why we talked about how to find it a couple different ways at the beginning. So what is the maximum or minimum going to depend on? Obviously the vertex, but also the direction. If it's facing up, it will go up forever, which means we will have a low point, a minimum. So again, that depends on the a. You will have a minimum when a is positive, going up. You will have a maximum when your a is negative or going down, because then if it's going in the negative direction, you will have a high point or maximum. Either way, that max or min will always be at the vertex. And you can give me the x and the y so I know the exact place the max or min is at, or you could even just give me what the min or max is as a y value. Okay, it just depends on how they ask the question. If you want to play it safe, give me the exact point. So I mentioned that there could be 0, 1, or 2 x-intercepts, places it crosses through the y-axis. Because it goes up or down and out forever, there will always be one and only one y-intercept. But sometimes these things will be above the x-axis and going up, or below and going downwards. So it never crosses through, therefore there is no x-intercept. There's a special case that our vertex is actually on the x-axis, and therefore we'll have one, or what happens most of the time, it's below going up and hits 2 places, or it's above going downwards and hits 2 places. This is what happens most. Then there's these 2 special cases, right? So make sure that you know most of the time you're going to get 2. Every once in a while, you'll get none or 1 for where it intercepts or crosses the x-axis. So let's make sure that we know how to find these things, right? I want you to find all. Rather than doing an example of each type, let's just do it for all of them. Let's make sure that if you are given an equation, quadratic equation that is, if you are given an equation, a quadratic equation, can you find the x and the y-intercepts? Can you find the vertex, axis of symmetry, max or min? I want all of that. So rather than doing one for every type, let's just find them all for one example. So how are we going to start? It's up to you. My suggestion is start with what gives you the most, and that is the vertex. And then also to graph it, the main thing to doing most of that is the vertex. So let's find that first. And because this is in general form, we're going to use that -b/2a to find our x of our vertex, that y value. Excuse me, that h value. So careful. I always put parentheses whenever I'm plugging things in. What is my b? It's a positive 2. And my a negative 1. Be careful with your signs. You don't want to make mistakes. These things down here are not adding or subtracting. It's 2 times our a. It is negative whatever our b is. So the opposite of whatever your b is going to give us a negative 2 over a negative 2. So we just found that our x is positive 1, which actually gives me 2 things. It gives me the x of my vertex and the line of symmetry or axis of symmetry as the equation that it is. So now all I got to do, since I know what my x is, I will have to find what my f of x or y value is by simply plugging it in. So remember, anytime I'm going to replace things inside of my equation, I like to put parentheses so that I don't make any mistakes. And since we found our x is 1, I'll replace everywhere we had the x with a 1. So careful, order of operations. This is not a negative 1 that is being squared. It is a 1 that is being squared, and then we're going to take the opposite of it. That's what this says. So be careful. So that gives me 1 squared, which is 1, times a negative, which is negative 1. 2 times 1, 2, plus 8. So that is a 10 minus 1. I just found my y is 9. So now I should be able to tell you what the max and min are based off of my vertex. And I also should be able to tell you the domain and range now that I have my vertex. Just be careful. What direction is this one facing? Good. Hopefully you said downwards. Negative. So I know I'm going to be shifting the original x squared by going right 1 and up 9 when I go to graph this. And then it's going to be facing in the negative direction. We'll have to find where that hits on our x and y axis in a minute. But for now, I want to show you, you don't need your graph to answer all of this stuff. Got my vertex, axis of symmetry. Because it's facing downwards, we're going to have not a minimum because it goes down forever. It's a maximum at the point of my vertex, 1, 9. Also, I can visualize that this is going down forever. And since it goes down and out, we said the domain of every quadratic function is, negative to positive infinity, not including. And our range depends on both the direction and that vertex point. And since we found our vertex is here and we're facing down, our range starts at negative infinity and goes up until a y value of 9, which is what we said our maximum would be at. So here's the last part before we graph. How are we going to find our x-intercept or seps and our y-intercept? And which one do you guys want to find first? Probably whatever one's easier. And if you guys notice, they already told us what f of x or y is. All I got to do to find my y-intercept is let x be 0 to find my y. And when you let x be 0 here and there, it's going to wipe all of this out. And therefore, my y is 8. But it takes a little bit more effort to find your x-intercept or seps. Because in order to do that, we're also going to let the other letter equal 0 and try to find the x or x's. And in order to let y equal 0, that means we now have negative x squared plus 2x plus 8 equals our y, which is 0. Hopefully you guys remember how to solve quadratic equations. I gave you a hint up here. You can use factoring, which is what you should always use first because it's our quickest, easiest method. And if that doesn't work, you should hopefully know the quadratic formula and how to complete the square. Your choice on which one. Most people just opt for this because it's less thinking, but it is also longer most of the time than doing this. It's up to you. I'm going to try to factor first because it's my quickest, easiest method. And in order to do that, I'm going to multiply through this equation by -1 because I can. I can do whatever I want as long as I do it equally to everything. And that looks a little bit better. Now I'm not starting off with the negative. So now in order to factor, I know it's my trinomial because there's no GCF. I know x times x when I FOIL distribute will give me my x squared. I'm thinking what gives me a -8 is 2 times 4. And because it has to be negative, I know one of these has to be positive and one has to be negative. It's the only way to multiply to get that -8. I just got to make sure that when I do FOIL distribute this out, and that gives me the 4x, and that gives me the 2x, that I choose which one is positive and negative to get that -2x in the middle. So I know my signs are different, and I know my bigger sign has to go with the negative. So my guess is that we are going to put the negative here and the positive there to get my x squared, to get my -8, but we got to check to make sure we get the -2x in the middle. So the x times -4 and the 2 times x does in fact give me my -2x in the middle. So I factored it appropriately. Now all I got to make sure is, do I know what times what gives me 0? And the only time something times something is going to give you 0 is if one of these factors is 0. And what plus 2 would make that 0? Hopefully you said -2. And what minus 4 would give me a 0 for x? The other one would be 4. So we just found our X-Intercepts. There's 2 of them. Would be at -2, 0 and 4, 0. And with all of this information and the fact that I know that this faces downwards, I should be able to graph this pretty well. So let's apply all of this together and draw this out real quick. And let's start with that first thing, that vertex, 1, 9. From there, we knew that it was facing down, and it was that normal x squared with some shifts going on. And we know the shifts are right 1, up 9. We've already done that. So since I know it's my normal negative in this case, which is going to make it down instead of up, but my normal x squared, I know when I go right 1 and left 1, I will square it. And in this case, go down 1. If I go right 2 and left 2, I know when I square it, it'd be 1, 2, 3, 4. 1, 2, 3, 4. And that should be enough for me to graph. Pretty good. Boom, draw it. But remember, we wanted to be more exact. And don't forget, we just said that our y-intercept would be 0, 8. Check it out. 1, 2, 3, 4, 5, 6, 7, 8. We also said our x-intercepts would be at -2, 0 and 4, 0. So if I kept going out 3 and then down, you would see I would be right there at my 4, 0 and -2, 0. So now I have a more precise graph for this quadratic function we call a parabola. Now, don't forget, if you are going to draw in that axis of symmetry, that line, then it has to be dashed. That's just a way to make sure that we graph this appropriately as far as our width goes, but it's not actually a part of all of the solutions, which is why we graph. It represents all the solutions. We're showing them to this original equation. All right. So that's it for this section. In a nutshell, everything in one example Hopefully we don't have a lot of those, but if you were to be asked any of those questions, you should be able to individually find and solve any one. Pay attention to the details. Take it nice and slow until you get the hang of it. All right? I'll see you for the next one. Hey guys, Alan. Round 2 of chapter 5. We're going to talk about power and polynomial functions. Okay, this is the start to a very important part of this chapter in this class as a whole. The better that you can understand some of these concepts and the deeper, the better off you're going to be in calculus. So remember, pay attention to the details and really try to understand why things are what they are, and then obviously how to use them. All right, so we're going to just first classify what a power and polynomial function is, and then we'll get into more details with them. Power function, named aptly after anything that has x raised to a power. Now, of course, it can have a coefficient in front other than 1, so that's what the k is there for. All right, but remember, power functions have x to a power. Okay, do not get that confused with when we have a function where it's some base to a power of x. Okay, that is what is called an exponential function. Okay, when our x is up in the exponent. So make sure that you know the difference between an exponential function and what we are now calling a power function. All right, well then, what kind of functions are labeled as power functions? There's quite a few, actually. Let's take a look at this list right here. This is called a constant function, whether it's 1 or anything. If we have y equals a number, then it is constantly and always that number for y. How about the identity function when x is equal to y? Or the one we just reviewed in the previous video, x squared, the quadratic, the cubic, the reciprocal, or the reciprocal squared, square root, and cube root. Here's a bunch of those basic toolkit or parent functions that we talked about and graphed earlier. Well, which ones of these would be considered power functions? According to the definition, all we have to be able to do is write it as x to a power. So obviously, which ones are power functions? That one, and that one, without a doubt. You can see that this is x to the first, x to the second, and x to the third. Those are definitely power functions. But what about the others? Could I write this as x to a power? Or any of these? They definitely have x's in them, but can we write them in terms of x to a power? Well, the answer is actually yes. And you're like, to which one? The first one? How can I write that as x to a power and it still be equal to 1? Hopefully you remember that anything to the 0 power is actually 1. So this too would be what is called a power function. The only thing that can change is the constant. Say it was a 4 instead. Still have x to the 0 there. And therefore it fits that criteria for the definition of a power function. But what about these reciprocal or reciprocal squared or square root or cube root functions? Can we also write those as x to a power? The answer is also yes. How, you might ask? Well, I can see I have here x to the first, here I got x to the second, and all I want to be able to do is write it as x to a power. Well, if I need to take this x to the first and move it to the opposite side of my division bar, hopefully you remember that would be when we take a negative exponent. So whether it's a 1 or a 2, you should remember that when we have a negative exponent, we moved it across our division bar and it became that. Or if it was squared, cubed, etc. So to add to our what is already long list of various looking power functions, which also have their more individual name. We're going to add those two, but what about the last two? How about a square root or cube root? We can't just get rid of those, right? Well, some of you may remember that to take a square root, we need something squared. That means we need it times itself twice, or in this case, if it was cubed, 3 times. Well, then, if we have a square root of x, you know that the square root of x only has one of them in there, and we needed 2. So in other words, we have 1/2 of what we needed. Or if it's a cube root, we need 3 of a kind, 3 x's multiplied together. Well, then that means we only have 1/3 of what we needed. So, of course, that means that we can rewrite these as well as x to a power. So every single one of these types, constant, identity, quadratic, cubic, the reciprocals, and square and cube roots, or nth roots for that matter, are all what could be considered power functions. Because we can, even if they aren't already written as x to a power, get creative and write them that way. All right? So why are power functions so important? Well, we need to talk about this new thing called end behavior. And what do we mean by end behavior? Exactly that. How do these things behave at the ends, the outer parts of all of their graphs? So as you saw in the previous example, these power functions can have x to many different powers, 0, 1, 2, 3, or -1, -2, or even a fraction. Well, then we're going to focus on whether or not they're even or odd, because hopefully you remember quite a few of these, if not all, of what the parent or toolkit functions look like graphically. And remember, I told you when we were doing those, the better that you can just know them and remember them right off the bat, the easier it is going to be down the road. Well, here we are. What happens when you have any of these and you know that this looks like that, or this looks like that? Then you know how it behaves in the end. Now, if I wanted to take this parabola, quadratic, power function, and I wanted to make it go the opposite direction, all I'd have to do is throw a negative in front. So it matters whether that k in front of our power function, that constant, is positive or negative. Because if it's an even powered function, then we know that if it's positive, it's going to be facing that positive direction. Where if it's negative, then it's going to be facing the negative direction. And you guys have probably played games before. When the score is even, then that means it's the same, right? And you want to think of odd as opposite. So even, same direction, odd, opposite direction. Now, how are we going to tell for when it's positive versus negative? Well, obviously, it's pretty easy to see that when it's even and positive, it's facing both the same direction and up. When it's a negative in front and it's even, then it's facing down. But what about odd? When it's facing opposite directions, well, remember how we read was along our number line first. And we always got larger from left to right. So that's the way that we also read books. That's how we're going to read these graphs, from left to right. And what we're really talking about, if we're looking left to right, is how do the y's behave? And as you can see, my y values are getting bigger and bigger and bigger. We call that an increasing graph, right? Which means when it is an odd power function that has an even coefficient in front of it, from left to right, it's going to end up being the positive direction. From left to right. But when it's negative in front of that odd power, that means we're going to end up from left to right going in the negative direction. So even are always going to face the same. The odd are always going to face opposite. And how do we know if they're both up or down if it's even? We look to the front of that power, the coefficient k. If it's positive, it's going to be facing the positive direction. If it's negative, then it's going to be facing the negative direction. Where if it's odd, then we know if it's a positive odd power function, then it's going to, from left to right, end in the positive direction on the far right. Where if it's negative, from left to right, negative. So this end behavior is going to really help us to know how the ends behave, for lack of a better term, because we're going to be focusing in on a lot of this little window of some of the key things like X and Y intercepts. Okay, the domain and range will come into play with this stuff. And how are we going to say all of this stuff without having to show you? Or if they show us, how can we tell them how it behaves on the ends, the far extremes? Well, we're going to say with these arrows, it's going to mean what it approaches. That's what that arrow means. So as X approaches negative infinity, can't ever reach negative infinity because that's an idea. It's not a thing that we can put our finger on. But as X approaches the far left, what do my Y values approach? Well, in this case, it'd be positive infinity. Where if the X approaches positive infinity, what do my Y values approach? Also positive infinity, if it's an even positive power function. Where if it's odd, we know when we go to the far left, we are going to start downwards for my Y values, negative infinity. And when we approach the far right, positive infinity, what do my Y values approach? That would be positive infinity this time. Where if it's the even with the negative in front, then they're both going to be facing down. So as my X goes to the far left, my Y goes to the far left. As my X goes to the far right, my Y approaches negative infinity. It goes down as well. For an odd with a negative in front, it's going to go downwards, which means to the far left, as X approaches negative infinity, my Y values would be way up here eventually, meaning positive infinity. And when I go to the far right, it's going to hit negative infinity. So as my X approaches the far right, my Y approaches negative infinity. That, my friends, is what is called end behaviors. And it is very simple to know when and where it does what. It's just going to take us some getting used to writing it in this weird form. Okay, but you'll get there with practice. Just remember, practice makes permanent, not perfect. Perfect practice makes perfect. Okay, but whatever you practice, paying attention to details, being disciplined, if you practice that, then that's what's going to become permanent. Okay, so practice the way you want to behave. And that's what we're looking at, is how do these things behave based on the coefficient and that power. So now let's talk about polynomial functions, which are like power functions, but with more baggage. Check it out. Get rid of all of that stuff. Power function. Add and subtract some more of these x values all the way on down to a constant. Now it's polynomial. And if you break down the word polynomial, it actually tells you exactly what it means. Poly, meaning many, nomial, meaning terms or names. So polynomial actually means many terms or many names. There's many things going on. One, bunch in here, 2, 3, 4, can be however big. Now remember, we got monomials, binomials, trinomials. And after that, we're like 3 is enough. Anything 4 and above with the number of terms, poly. It's got many. All right. We're still going to focus on that highest power. And that highest power, which is usually the first thing that we write down, because we want to all write the same things the same way. So even though they might jumble these things up, we always like to write it in what is called descending order. The highest exponent on down to no exponent. So 3, 2, 1, 0, for example, or 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, however many there are. That first thing we're going to call the leading term, and whatever's in front of it, the leading coefficient. And so that we know, just like without all of this, what the power would be, we're going to call it the degree of the equation or polynomial. And what, might you ask, is the significance of the degree? Why do we give that a special name? Does anybody know? What's that? I can't hear. I'm kidding. This is a pre-recording. Yeah, I just wanted you to think about it. What is the significance of the degree? It tells us how many possible solutions, x-intercepts, zeros, there are for that equation. So if you take this polynomial and you let y equal 0, which, by the way, if you're letting your y equal 0, that means you're finding your x-intercepts, which we also call zeros because that's how we find them. They're also called solutions to the equation. Okay, many different things for the same thing, just depends on the circumstance. What are we looking to find? That degree will tell us how many there are possible. Now it can be less, but never more. Right? Why can it be less? We can have repetitive things. Like if I had x plus 2 quantity squared, and that was my function. You know, graphically it's a parabola, and there would be a shift of -2, but no y value. And so there's actually 2 solutions to this, but they're the same. So there can be repetitive things, which we'll get into a little bit later and see how we can use those to our advantage as well. All right. Almost done here. Let's talk about what else we can find in these polynomial functions. Well, these polynomial functions are going to be similar to some of those power functions we just reviewed, but they're going to have more of what are called turning points, right? When we have a cubic function, something like that, you can see that I had to turn how many times in order to graph this. Well, I started down here, went up to a point, and then started changing directions, went down to a point, and then started going back up forever. So there are actually 1, 2 turning points in this cubic function. Now again, there can be more stuff, but we know it's cubic and it's positive because it ends with the positive from left to right. What about a parabola? Let's just go upwards. How many turning points does this have? Well, hopefully you can see there's only one. We went down, 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 down to a point and then up indefinitely. Decreasing here, increasing here. But there was a point where it turned from one to the other. So hopefully you're noticing a pattern. When we had a degree of 2 in our polynomial, there was 1 turning point. When we had a degree of 3, there was 1, 2 turning points. And if we had 4, there would be 1, 2, 3 turning points for a polynomial with degree 4. So as you can see here, a turning point, which is where our graph changes direction from increasing to decreasing or decreasing to increasing. There will be a maximum of n minus 1, where n is the degree of that polynomial. And if we wanted to talk about the places that it crosses through the x-axis, where these things were equal to 0, we can also do that by, again, letting our y be 0. And again, if we have a degree of n, then we will have that many possible x-intercepts, like we talked about up here. That's what the degree tells us, how many possible x-intercepts or zeros there are. Right? Now, I also want to mention, like I did up there a minute ago, this thing called multiplicities. When we have more than one, zero x-intercept or solution, right? We'll talk about that more in 5.3, but I did want to mention it to you already. It's something that we have talked about when we get there. It's when we have a multiple, because remember the degree tells us that there are that many solutions or x-intercepts or zeros, whatever the degree is, and one less for our turning points. And the importance of turning points are, if we look at them again, remember we talked about local maxes and local mins? That's where those turning points are located, at that locally around it highest point or lowest point. Okay, and again, those are so important, those points, that we're going to call them critical points in calculus, because that's where we can find some maximums and minimums. And when we set up functions based off of stuff we've known and seen in the past with our business, and we can then graph them to try to figure out where a certain price point would be to maximize our profit or minimize our costs, that's where this math can come in real handy to apply to the real world. So let's do a few examples. Make sure that we understand this. If you want to pause it right here and try these before I go over it, please do. I encourage you to try that first. If not, I'll continue on, walk you through these so that you can hopefully then do both your homework and group quizzes and get that practice to make this much more comprehensible than it may have been before. All right, hopefully that was enough time to give you guys a little bit of time to pause it and try it on your own. Let's make sure we answer the questions that they asked. Without graphing, they want us to determine the number of x-intercepts and turning points for this function. Now, I will warn you, as I have already, they will not always put it in descending order to try to make sure you're paying attention to details. It's not whatever's first that is your leading coefficient. If I was to rewrite this function, I would find the highest exponent first, which would be x to the 12th, and that's what I would write down first. Because all the other stuff in these polynomials, to answer these questions, which was find the maximum number of intercepts and turning points, that's the only one that actually matters. And not just its power, but also its coefficient. So help me out. Help yourself. How can we find the maximum number of x-intercepts? What did we say that was dependent on? Hopefully you said in the degree of this equation, that highest exponent. And what about turning points? What did we say that one would be? That was n minus 1. So our answer to each of those is the max number of intercepts. And I'm going to write x-intercepts just to clarify. Would be our degree of 12. And therefore, the max number of turning points would be 1 less than that in 11. Now remember, it can always have less, and that's where those multiple solutions, those repetitive solutions come into play. And we'll talk more about that in a few weeks, in a few sections. Okay, so that's it for the first one. Not a whole lot to it, just trying to make sure that you comprehend what these things mean. Now let's apply it to this last example. Given this function, 2x cubed minus 6x squared minus 20x, let's see if we can find all of the things that we just talked about. The leading term, degree, the end behaviors, and any of those local behaviors as well. All right, and then our local behaviors, along with the leading term, degree, end behaviors. The local behaviors meaning What are the things locally that are in close in the middle, not just the extremes? So our X and Y intercepts and the maximum number of turning points. You'll learn in calculus how to find those turning points, those local maxes and mins, a heck of a lot easier than we can do without calculus. Okay, so for now, we'll just talk about how many there are possible. In calculus, we'll find them exactly in a little bit more detail. So what is the leading term? Let's see. What did you guys come up with? Well, make sure just because they listed it first doesn't mean it's always our leading term. It's whatever the highest exponent, the degree of our equation is. And this one is 3, 2, 1 written in descending order. So we're good. The first thing that we should put is 2x cubed, which means our degree is 3. That is our highest exponent, and therefore a third degree or cubic polynomial. And just based off of that information of my leading term, I should be able to tell you how the ends of this thing behaves. Because it is a cubic function, if I forget about the shifts and all the other things that that's going to affect, thinking about my power function, this is definitely an odd power. And therefore, it's going to have opposite behavior on the ends. And from left to right, because I know it's a positive, it's going to start negative and then go up positively. Which means as my x approaches the far left, what does my y do? And then as my x approaches the far right, and you don't need to put the positive, it's just for emphasis, what does my y do? Well, I know that my y approaches, when I go to the far left of my graph, it was going to be somewhere down here, indefinitely. So negative infinity. Where because it's a cubic and it's a positive, we knew that it, as we went to the furthest right that we could think of for our x, our y's increased to a maximum. Maximum, because it continues on forever. That's the symbol we use, is an 8 taking a siesta. That is infinity. Okay, now what about our local behavior? How would we find our y-intercept? Well, if I want to know what my y is, I will let x be 0 and then find it. The beauty of it is, it already tells us what y is equal to. All we need to know what x is. So we plug in our 0 for x everywhere we see one, and you can see that all of this would wipe out to be 0. We're at the origin, 0, 0. How do I find my x-intercepts? A little bit more work. How do I know how many there are? Well, remember, the degree tells me how many there are possible. There are 3 possibilities, but we can have something repeat. So there could be 2, could be 1, could be none. Everything could be above, but not likely because of the arrows. If it's a parabola, different story. But because we have a cubic, they're going to face opposite directions. We know we're going to at least have to cross through somewhere, whether it be here, here, wherever. How do we find those x-intercepts? We let y be 0. And we'll see how many there are if there's more than one. We'll go up here, we'll let our y be 0, and we will solve this. So I will take my 2x cubed minus 6x squared minus 20x, and I will set it all equal to 0. And remember, our quickest, easiest way to attack these problems is by factoring. And hopefully you remember the first rule of factoring, GCF. What do all of these have in common? Not just the obvious, which is an x, they also have a 2. And because we have an x involved, we can't just divide everything by 2x and get rid of it. Even though we can typically do whatever we want to an equation, we cannot get rid of things we don't know. We can't divide by zeros, and we don't know if that x is 0. Actually, we already do. But in general, can't divide by a variable. So how do we undo dividing? We multiply. It's like we're actually multiplying this whole thing by a fancy 1 of 2x over 2x to each one of these. We call that just factoring it out. And then we do the dividing to each of these by the 2x. But we have to have that on the outside. So when I divide this by 2 and x, I get an x squared minus 3x minus 10, all still equal to 0. And just because you factored out a GCF does not mean you get to stop. You have to keep going. And in this case, we're going to still have that 2x on the outside. Don't lose it. But I'm going to try to factor the trinomial that's left on the inside. I'm good at trinomial factoring. You should hopefully be by now too. If you've gotten to this level of math, this is one of the key concepts that will never go away. I'm thinking 5 and 2 that multiply to 10, and a -5 times a +2 not only gives me -10, but it combines to -3 in the middle. Now this is where people get a little lost, not paying attention to details. How many factors do we have right now? 1, 2, definitely, but a lot of people lose that GCF out in front. You actually have 3, just like we said the degree of the equation was. And so therefore, there are 3 possibilities to making this thing equal to 0. And that's when 2 times something, x minus 5, and x plus 2 equal 0. So that yields an answer of 0, 5, and -2. So I actually have 3 zeros or x-intercepts. So I'm going to need all 3 parentheses. Where the y was 0, we got x values of 0, 5, and -2. And because we know the degree is x cubed, we know the maximum number of turning points, there can be less again, but cannot be more, would be n minus 1 or 2. And now that we found all of those things, how it behaves on the extreme or ends, what some of the local points are, and how many places it changes direction, we should be able to graph this. So let's do it. What would the graph of this look like? Let's graph it real quick by starting with labeling these points that we already know. The 0, 0, which was both an x and a y-intercept. The 5, 0. The -2, 0. Those are all my x-intercepts, and that also was my y-intercept. And then from there, we also knew, because the leading term was positive and x cubed, that in the extremes, we knew that to the left, it would start in the negative direction down here. And to the right, it would end up here. And therefore, we knew that it had to cross through this, eventually turn, come back down, hit this, eventually turn, and then hit that and go up forever. And that, my friends, is what the graph of this would resemble. Now, did it exactly go up that height or down that low? Did it hit right here? Was that the right x where it started changing? Well, I will let you know, usually it is in the middle of those. But is this the right height for my local max and local min? I don't know. And I don't care when they ask me to sketch. Okay, if you wanted to check it out, go to a place like Desmos, Graphing Calculator, GeoGebra, and actually plug this in. And I'll show you real quick what that would look like. And you can see I was way off, but I got the right sketch resemblance of this, where it had those 2 turning points, but one of them was way down there at what looks like -60 and all the way up at 11. But you can see that that turning point there is at, or excuse me, my x-intercepts are at that -2, 0, and 5, just like we had on our graph. -2, 0, and 5, with my 2 turning points in my end behavior. Okay, keep practicing at this stuff. Really try to understand why you're doing what you're doing, so that then when we add more things to this, it will be pretty simple. And like I said, we'll be able to find more of these exact values, those critical points of where the heights of the max and the min are, using calculus when we get there. That's all I got for you. Hopefully you enjoyed that. Short and sweet, just like my wife. Keep it classy, students. Keep working hard. I will see you at the next one. Adios.